Right, okay, so for this problem, it's deliberately left as part of the exercise for students to make their own little roadmap here, right, and figure out, wait a second, which one comes first, and what does that mean about which variables are playing what roles, right? But I will make an observation that something that's going to be true for all of these is we have a confusion of variables problem, and that's explicitly, indicated here. Make sure you don't confuse variables, right? So let's look at the, I'm just going to do part 1 here, and notice that in part 1, and I'm going to build my little roadmap right here, G acts first, and then subsequently F acts on the outputs. Whatever comes out of G is what F acts on, right? Okay, so we're going to have a confusion of variables problem if I use the same variables for the input of G and for the input of F, then I'm using then the same variable for what goes into G and what comes out of G, and that's not okay. Right? Okay, so something's going to have to get rewritten. Doesn't really matter which way we do this. Arbitrarily, I'm going to leave G written in terms of X and Y. And then I'm going to say, so in other words, we'll be leaving this like that. But I want to rewrite this function. I want to rewrite it in terms of 2 other variables. And you could use U and V or S and T or whatever. It doesn't really matter. I'll use U and V, no particular reason. Okay. All right, so is everybody good so far on why I have to rename? And okay. All right, so now let me explicitly rewrite what that function is. F, I guess I'll do it in red here. So F of UV is U squared minus V squared, and then 2UV. Now, keep in mind, all of what we're doing here makes sense in the context of that specific part, right? And if you look at number 3, then you've got to make different choices. All right. Okay, so we've got our little roadmap. F is a function of U and V. U and V are G, which are functions of X and Y. By the way, let's add that to our little thing. U and V are the outputs from the G function. So let me explicitly put on here, that's U, right? And that's V. Is that cool? Yeah. Just because it's easy to lose track. I mean, there's a lot of variables running around, and it's easy to sort of lose track of what's what. Okay. All right, compute derivative matrices for the following compositions. Yeah, so at this point it becomes a Jacobian problem. We're looking for the composition here of F composed G. So that's going to be Jacobian of F times the Jacobian of G. And now let's start taking derivatives. Well, let's at least write down the partials. Let's start with Jacobian of F. And don't forget what F is. F is that right there. All right, so I've got to take partials with respect to U as my first column, partials with respect to V as my second column. Okay, so U partials gives me 2U, 2V. V partials gives me minus 2V, 2U. Okay. Jacobian of G. Alrighty, well, the Jacobian of G, come back up here. There's G. Got this formula for it. And I got to take partials with respect to X and Y. All right. So first the X partials. The x partials of these functions are y and 2. And now the y partials are x and minus 3. And you can multiply this out. Is that cool? Don't forget, you do have to sort of, rewrite your variables. We've been asked about. I got a huge mess going up here. Let me clean up my huge mess. I've been asked about this composition. That's F compose G, is that composition there. The input variables are x and y, so I've got to rewrite everything in terms of x and y. And notice that this tells me how to rewrite u and v in terms of x and y. So everywhere I see a u, I've got to put x, y. And likewise, everywhere I see a v, I've got to put 2x minus 3y. So this will be changed accordingly, and then notice that multiply this out, make those substitutions, and you'll have a great big matrix that's in terms of x and y as needed. Everybody happy with that one? Okay, so the other parts are similar. The one twist is the last one. You're composing 3, which means you're multiplying 3 matrices, which means also that you're going to have to, in fact, it will be like this. Having H there at the end means that there will be an H over here like this. So you're going to have to rewrite H in terms of new variables. And so, for example, color choice. I was running out of colors. Here, I'll do red. Maybe S and T. You're going to have to rewrite H as well. And then, again, make sure to keep track of what's a function of what, what's which given function of what other variables, and the answer to all of these questions is made clear by having a good little roadmap. So I'm a huge believer in this little cheat sheet that keeps track of everything like this for you. And you develop it as you go along. Make sure to represent all your choices accordingly.
How would you do the cross multiplication? Like, we do F and G first and then...
Oh, so it turns out matrix multiplication is associative. So it doesn't matter which order you do the actual multiplication. Now the matrices have to be written in this order.
Yeah.
So the Jacobian of that composition is going to be Jacobian of H, Jacobian of F, Jacobian of G. But if you want to group it like this, fine. If you want to group it like this instead, okay, doesn't matter. You get the same answer either way. Yep.
Can you just use the answer from 1 and just multiply that by the Jacobian of H?
Yeah, I think that'd be a reasonable choice. Yeah, absolutely.
And H is like actually giving out just like 1, 1, 1, -1. Like there was no variable.
H is a nice, easy matrix.
There was
Yeah,
no
that's
real variable,
yeah.
so
Well, yeah, but see, that's fine. I mean, if you think about it, I mean, so the derivative is constant. Is that a problem? No, it's great. I mean, go back to single variable calculus. There's all sorts of functions whose derivatives are constant, right? And it's good news. It's a good thing, not a bad thing. Is that cool?
Yeah.
Everybody happy? Okay.
Can we do the number 8?